Hi everyone, it's Mr. Baker here. Today we're going to be looking at stability. So we're going to be looking at stability today. Now, when I was a kid, I had one of these things. It's called a Weeble. I don't know if you all know what they are, but there was a whole sort of thing you could have when I was in. This is probably when I was about 4 or something. I don't know. When I was really young, and you could sort of get all these different things to do these Weebles, and you could push them, you could play with them, but these Weebles would never fall over. So the question today is, why do Weebles wobble, but they don't fall down? So we're looking at stability today. And stability is a measure of the body's ability to maintain its original position. So what two things can change an object's stability, do you think? Well, I've given you a bit of a clue by those two triangles that I've drawn there. So we've said stability is a measure of the body's ability to maintain its original position. So the centre of mass, if we lower that, then that will change the stability. So on the left-hand diagram of the triangle, the centre of mass is quite high, but on the right-hand one, the centre of mass is quite low. And which one's going to be more stable? Which one's going to be able to maintain its original position easier? Well, yeah, it's the one on the right with the lower centre of mass. The other thing that changes the stability of something is to do with the area, the base, or the area of the base. And if that's really wide, then that will also make it really stable. So why do you think these two things are? We will explain them as we go through today. So have a look at these 4 diagrams here. So we've got a block in its original position. Then we've got positions A, B and C at different sort of topples, I suppose. And what do you think might happen to them? So you might even want to do this. Describe what you think will happen in each diagram at A, B and C. And then if you can explain your description in terms of moments, that's perfect. Okay, so you might want to do that. If you do, then pause the video and you can have a go, and I'll go through it with you in a second. Okay, did you do that? Okay, well, let's have a look. So in its original position, obviously it's just there on the ground. In position A, it's not going to topple. It will go back to its original position since the line of action from the centre of mass lies within the area of the base. This causes an anti-clockwise moment around the pivot, resulting in it turning in this direction. Okay, so the centre of mass is just there, and the weight is pulling down from the centre of mass, and that arrow, that line of action pulling from the centre of mass, is in between the area of the base, and so it's going to go back to its original position. So let's have a look at position B. So this one here won't topple, I suppose. Right, so in this position, it's balancing. The clockwise moments and the anti-clockwise moments will balance, resulting in equilibrium. So because this arrow is going right over the pivot point, and it's the centre of mass, then actually this will be balanced like this. So it's not going to topple. It's not this. I mean, if this was its original position, then I suppose then it wouldn't topple either way. It wouldn't take much for it to topple to the right or to the left, would it? There, because it's balanced right on the pivot point. And then on C, well, this one is going to topple. There's a clockwise moment around the pivot, resulting in it turning in this direction and falling to the side. Okay, so we have said that stability is a measure of the body's ability to maintain its original position. And then we've said that if you lower the centre of mass, or if you make the area of the base really wide, then you will have a more stable object. So let's see if we can explain why that is. So lowering the centre of mass, if we do that, then a lower centre of mass will allow the line of action to act within the base area of an object. The area of its base should be as wide as possible, so that allows the line of action to act within that base area. So both of those things will make something stable. Lowering the centre of mass will mean that the line of action is going to be within the base area, and making the area of the base larger is going to allow that arrow of that line of action to act within that base area. So both of those things will make the object more stable. If the line of action And the reason for both of those things working is that if the line of action of the weight of the body lies outside the base of the body, there will be a resultant moment and the body will tend to topple. Okay, let's look at an example then of a double-decker bus. So double-decker buses must be tested for stability. They've got to go around corners, they're quite high. Passengers have got to feel safe in them. You might have passengers at the top or the bottom, and we don't want them to topple over. So this is the kind of thing you might be able to do, and you might want to do this. So draw a diagram of a double-decker and its centre of mass, and explain why you think the centre of mass is where you've put it. So you might want to just do that. If you do, then pause the video. I'll go through it with you in a second. Okay, if you've done that, well, let's go through it. So the centre of mass is quite low down on a double-decker bus, and so the centre of mass is down there, and the area of the base is there, and so this line of action from the weight from the centre of mass is within the area of the base, and depending on the speed that it might go, I mean, it's probably not ever going to topple and it's not ever going to go that fast around the corner, but this is why they test them, that if it was like that going around a corner, then even at a really high speed like that, then because the centre of mass is low down, then the line of action would still be within the area, and so it wouldn't topple over. It would take an awful lot. It would take you toppling the bus all the way over to that sort of steep angle before the line of action was outside the area of the base and would topple it over. What happens, do you think, to the centre of mass when all the passengers are on the top deck, and how would this affect the stability? So this is a kind of question that you might have to answer. So if you want to pause the video there and have a little go at that one. Shall we go through that one then? So if the passengers are all at the top, then that's going to make the centre of mass rise up, and if the centre of mass is risen up, then it's going to make the double-decker less stable, because it's easier for the line of action to be outside of the area of the base if the bus was at an angle. Okay, so that's pretty much the end of this lesson, and these are the things I think that you should be able to do. I think you should be able to describe how the centre of mass of an object affects its stability, and you should be able to explain toppling and stability in terms of moments and apply this to different situations. And one of those situations is a Weeble. So this was our question. I know you've all been waiting for the answer. Why do Weebles wobble but they don't fall down? Right, so have a look. This is the explanation. This is the innards of a Weeble, believe it or not. So the grey material is of higher density than the red material, causing the centre of mass of the object, which is labelled C in our diagram, to be very low. So the centre of mass is low. This means that when the Weeble is wobbled, as in position B, the centre of mass will be on the other side of the pivot point where the Weeble is in contact with the ground, and so gravity will cause it to return to an upright position, and so our Weeble will wobble, but it won't fall down. Whee! So that's the answer. I've been Mr. Baker, and this has been all to do with stability, and I will see you next time. Thank you very much.